Okay, so today I don't have very long, so I'll just introduce what mid-infrared polarization can tell us. And the key thing is that at these long wavelengths, scattering is generally unimportant, at least in bright regions where there's strong dust emission. And so if we have aligned non-spherical grains, they have a larger cross-section along the major grain axis, which then means that we get emissive polarization from warm grains and absorptive polarization from cold grains that are along the line of sight in front of an emitting source. And for emissive polarization, the spectral signature is just the difference between the emission in the two cross-sections. But absorptive polarization, there's an additional term which is essentially the flux spectrum. And so the mechanisms are very different spectral signatures. And that's important because we can use that to determine which mechanism is dominant. And if the grains are aligned to the magnetic fields, then we can infer the direction of the magnetic field projected onto the plane of the sky by measuring mid-infrared polarization. And in those cases where a single mechanism dominates, either emissive or absorptive polarization, then we'll expect to see a constant position angle if the magnetic field direction is also constant. Now, most of the polarization measurements that are available at mid-infrared wavelengths are more than 20 years old. And here is an example of two objects, two high-mass protostars, the BN object in Orion and AFGL 2591. And they both have substantial silicate absorptions. You can see the 10 micron absorption here, the 20 micron absorption here in both cases. And there are corresponding polarization peaks to the 10 and 20 micron polarization absorption features. But notice that in AFGL 2591, there's a small inflection here at 11.2 microns, but that has a corresponding quite pronounced polarization peak. Also, the position angles in both of these objects are constant, and that tells us that we have a single mechanism operating. And in this case, it's polarization through dichroic absorption. If we look in more detail, here we can see the differences in the 10 micron spectra. And the fact that this secondary peak is so pronounced, whilst the absorptive signature is relatively weak, tells us that the material that's producing this is of high band strength. And this, in fact, was one of the first indications of the presence of crystalline silicates, which was obtained through polarimetry rather than through spectroscopy alone. The current state of the art in polarimetry at these wavelengths is canary cam on the GTC. And here's a comparison between the polarization towards the BN object obtained during the canary cam commissioning and the old data from the UCL spectrometer. And you can see that the correspondence is actually, I think, remarkably good, but there are regions here, 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 and here where there are hints of weak structure, which, if we can observe a number of these objects, could then tell us about much more about the constituents of interstellar dust. Moving on now to look at interstellar polarization, I want to just illustrate what we can learn about the line of sight to the galactic center. So here is the intensity spectrum of Iris-3, an isolated dusty M giant, supergiant in the central parsec of the galaxy. And again, there's this pronounced silicate absorption, there's a constant position angle, and again, you can see this spectral signature of polarization peaking at 10 microns and then reducing towards the wings of the silicate feature. Also notice that in the silicate minimum, the flux, of course, is very low, a factor of 20 or 50 lower than it is in the wings. And that means that the polarization signal to noise in the region near the peak of the silicate feature is not very good. Nonetheless, we can see that the spectral dependence of the polarization is quite similar to what we saw towards BN, Although when you look in detail, you see that in the diffuse interstellar medium, the polarization profile is a bit narrower than it is in molecular clouds, which reflects the same things that we find in the intensity spectrum. IRS1 is the brightest source in the filaments in the northern arm, and again it shows a pronounced silicate absorption, but now with evidence of a turnover at the wings of the spectrum, which indicates that there are both emissive and absorptive components. And where we look at the position angle of polarization, we now see there's a pronounced rotation in position angle, so that in the deepest part of the silicate absorption, we have position angles moving up towards 180 degrees, whereas in the wings of the feature, the position angle is closer to 120 degrees. And the polarization, the spectral dependence of the polarization looks quite different than it did towards the protostars and IRS3. And that's because what we're now seeing is a combination of interstellar absorption, shown by this profile, at a position angle of about 10 degrees. So this is the same profile that was there in IRS3. And that's overlaying onto an emissive polarization signature, which has got this different wavelength dependence. And the combination of those two then allows us to fit the observed spectrum. So what this demonstrates is that if you want to measure the intrinsic, the emissive polarization in this region of the galaxy, and then if you make measurements out here in the 12 micron region, the emissive polarization is quite high, but the absorptive polarization is quite low. And on the assumption that the interstellar polarization is constant, it was then possible to make measurements of imaging polarization, which reveals this rather ordered magnetic field. So these vectors are the emissive polarization rotated through 90 degrees so that they point along the magnetic field directions. So there are these ordered fields in the northern arm, but much less ordered structures in the east-west bar down the bottom here. And so with CanaryCam, we were able to probe this at higher spatial resolution. And just to reinforce what Bernard was saying yesterday, going to larger telescopes, but retaining the diffraction limited sampling, you don't improve your surface brightness sensitivity, but what you do is improve your spatial resolution. And so here now is the intensity image. Here's IRS3, from which we get the interstellar polarization. This is IRS1, the bright peak in the filaments. And now if we overlay the polarization vectors onto the intensity plot, we can see now that the magnetic field structures are much more complex. That it's not just a uniform field coming down here, but in fact they're sort of wiggling round through these bright peaks. And if we then kind of plot up regions of coherent vectors, we can see there's a number of filaments coming through into the northern arm at different orientations. And where filaments at different orientations are superimposed, we get polarization nulls shown by the purple circles. And in the east-west bar now, we can see that in regions of low flux, we do see vectors predominantly along the bar, but again, there's other regions superimposed on top of them. So for example, this region is quite likely an extension of the northern arm, which loops round and then re-emerges in front of the east-west bar here. So I'm out of time, but I hope this gives you an idea of what mid-infrared polarimetry can tell us. It gives us information on dust grain alignment, on magnetic field configurations, on grain properties and material band strengths, and of course, polarization measurements at shorter wavelengths in the L and M thermal bands gives more information on icy grains or mantles and on the hydrocarbon grains. finally, I just want to point out that most published results are from instruments with a wire grid analyzer and ambient temperature waveplate rather than an optimized polarimeter. And so it is possible to make good quality polarization measurements if you're careful using just bolt-on components. And finally, if you want to know more about this, the Spectral Polarimetry Atlas published by Craig Smith gives us the state of the art 20 years ago, which is more or less still the state of the art now. And there's a recent paper by Drain and Hensley, which talks about what mid-infrared polarimetry can tell us about dust grains. And so I've done.
Thank you very much, Pat. Very interesting to see the crystalline feature there on the silicate band. That was very nice. Bernhard has a question. I will read it for you. So his question is, ELTs and their associated AO systems with many tilted mirrors are all but ideal for polarimetry. So usual dedicated polarimeters proposed for the ELTs are deferred to the second or third generation of instruments. So will the future of polarimetry be restricted to optical, exoplanets, far infrared and submillimeter wavelengths?
Well, CanaryCam is, as I understand it, still available on the GTC. The problem is, of course, that most of us can't apply it directly ourselves to GTC, so you have to do it through collaboration. But that is definitely the state of the art in mid-infrared polarimetry at the moment. And I'd encourage people to find ways to use that.